Okay, so welcome to our first live, maybe not live video for Calculus 1A. We are going to jump into 3.2, which is related rates. And when we get back from spring break, hopefully we'll be meeting with one another face to face again in the classroom. And the plan is to have the exam when we get back from spring break. So that would probably, for your class, since it's 2 days, will either be Tuesday, Wednesday, or Wednesday, Thursday. So it's not going to be the first class meeting when we get back. So, but it should be that week. So because of that, I'm just going to start jumping into new material, and the next new stuff is called related rates. So related rates are pretty much word problems, and we have different equations usually related to time. And so I'm just going to start pulling some problems out. I'm going to write on the whiteboard so you guys are going to be able to see what I'm writing. And you should still see my video. I'm not sure if I'm going to keep that on or not, depending on how things go. I could always just put a picture of me on that right-hand corner. Okay. And then also bear with me because I'm not good at writing on the screen, and I don't know how to do colors right now. So things are hopefully you're my second class today, so things hopefully will be better by the time I meet with you tomorrow. Okay, so area. So we know that area of a circle is pi r squared, right?
No. Oh, no, thank you.
Jason.
Okay. How long? Right.
Do me a favor, Jason, and just mute your.
Sure.
Thank you. Okay, so basically the question says, suppose that the radius r and the area a equals pi r squared of a circle are differentiable functions of t. So write an equation that relates dA dt to dr dt. So how can we write an equation that the derivative of our area with respect to time is the same and relates to the derivative of our radius with respect to time? And so basically we want to take the derivative here. And so we're taking, because it's an equation, we can take the derivative of both sides. So notice that we're taking the derivative with respect to time. And so kind of like what we were doing before with implicit differentiation. And so right now I'm just going to look at d dt of the area is equal to d dt of pi r squared. Okay, so when we take the derivative of a, again, that's a composition of a function in terms of time. So just like when we were using implicit differentiation, when we were taking the derivative of y, we had to put that dy dt after it because of the chain rule. Same sort of idea here. And so when I take the derivative of a, I know that that's 1, but because I'm using the chain rule, this is going to be 1 dA dt is equal to, and so now I'm taking the derivative of r, which is in respect to t. Pi is just a constant, and so I can keep pi out front if I want, times the derivative of r squared. So derivative of r squared is just 2r. But I just took the derivative of this, and r is with respect to t. And so I have to put the dr dt after it. And so basically, we just wrote an equation of the relationship between the rate of the area of this circle with respect to time to the radius of the circle with respect to time. Okay. And this is. So we're just going to start and just do a couple of easy problems, and then we'll jump into some word problems. Okay. And I'm trying to move things around. Okay, so I'm just going to read problems out of the book for now. I think maybe in the future I'll have things typed out and I can make it a little more smoother. Let's say, assume that y is equal to 5x and dx dt is equal to 2. Find dy dt. Okay, so we're assuming that y is equal to 5x. It gave us what the derivative with respect to dx dt is equal to 2. And we want to find dy dt.
Mm-hmm.
So Gary, do me a favor. Or actually, I could probably mute you. But mute your thing so I don't hear feedback as I'm doing it. But let me know if you have any questions, guys.
Yeah.
Okay, so we want to find the derivative of y with respect to t. We have what y is equal to 5x, right? And so we're gonna, just like we were doing before, we're gonna take derivative. And so if we take the derivative of both sides, remember now in this case, y is with respect to t and x is with respect to t.
Mm-hmm.
So derivative of y is 1. But it's implicit differentiation. So we get dy dt. This is equal to 5 times, so derivative of x. So derivative of x is 1, but this is a function again of t, so we have to rewrite dx dt. So it actually told me what dx dt is. It told me what the rate of change was of x with respect to t. It was 2. And so I can go back in here and I can replace what dx dt is with 2. And so doing that, we get dy dt is equal to 5 times dx dt, which we were given to be 2. So in this case, dy dt is equal to 10. Okay, so let's go a little further, or a little harder. Okay, so now let's say you have x squared plus y squared equals 25. Oops. And we're given that dx dt is -2. And so if x squared plus y squared equals 25 and dx dt equals -2, then what is dy dt when x is 3 and y is -4? So what is dx dt when x is equal to 3 and y is -4. Okay, so basically, see if I can, oops, sorry about that. We're taking the derivative of both sides. And we can, x and y are both with respect to time. So again, we're using implicit differentiation. And so when we take the derivative of x squared, well, that's just 2x. But we're adding in now dx dt. Plus, now take the derivative of y squared. And so derivative of y squared is just 2y. Again, because y in this case is in terms of time, we can write this as dy dt. This is equal to the derivative of 25. Well, 25 is just a constant. A derivative of a constant is 0. And so now it's asking us, what is dx dt? So we're trying to find dx dt right here, right? When x is 3 and y is -4. So just go back into our equation, let's substitute. And so we have 2 times x, which is 3, all times dx dt, which we're trying to find, plus 2 times y, which is -4, all times dy dt. So I just noticed there's some sort of error. So what is dy dt when x is 3? So that question was actually what is dy dt and not what is dx dt. That should have been a y here. And so because of that, I'm not trying to find that one. I'm trying to find what dy dt is. So this is equal to 0. But I know, whoops, sorry. Okay, so we have 2 times y. Y is -4 times dy dt, which we don't know what it is. That's what the one we're trying to find, is equal to 0. But we are given, right, what dx dt is. That's -2. So we have 2 times 3 times dx dt, which is -2, plus 2 times -4. Well, 2 times -4, that's really -8, so -8. dy dt equals 0. So 2 times 3 is 6. 6 times this -2 here gives me -12 minus 8 dy dt equals 0. So get dy dt by itself, we could add 12 to both sides of our equation. So we get -8 dy dt is equal to +12, adding 12. Divide by -8, so we get dy dt equals 12 divided by -8. So reduce it. 12 divided by -8, both have 4 in common, so this would give me 3/2, and it would be negative. I can put the negative out front. Okay. So basically, what is this? What is this telling us? Well, what is the equation x squared plus y squared equals 25? We got some circle, right? Some circle centered at 0, 0, radius 5. It must be spinning with, you know, at some rate of time. And so basically, it looks like we were trying to figure out what the rate of change was with our X value when we're given that the rate of change, or we're given those values, and we're trying to find the rate of change of our Y value with respect to time, given what the rate of change of our X value was, -2, at the particular point 3, -4. Get that? Okay. Now let's maybe do another one and okay, so sorry. Let me pull up another problem, but let's look at more like of a word problem. And so first thing I'm going to do is I'm going to read it to you. Okay. So it says the radius R and the height of a right circular cylinder are related to the cylinder's volume V by the formula V equals pi r squared h. How is dV dt related to dH dt if R is a constant? That's not really the one I wanted, but that's okay. Okay, so the radius R and the height h of a right circular cylinder are related to the cylinder's volume. Okay, so basically we have this cylinder. And we're given that the volume is equal to pi r squared h. So we have our radius R, we have our height h. And first says, how is dV dt related to the derivative of the height dH dt if R is constant? So any ideas? Oops, I don't know what's going on, but oh. Sorry, something's popping up on my computer. Let me make sure I have enough battery. Okay. I'm gonna pause for a second. I need to plug in my laptop or it's gonna die on me. So I'm gonna stop the recording for a second. Oops. Cancel. I'm going to pause the recording for a second. Okay, so we're looking at how is the rate of change of our volume with respect to time related to the height, the rate of change of our height with respect to time if R is constant. So basically R is not changing, that cylinder is not expanding, it's just constant. And so same kind of process that we were doing before, we want to take the derivative. So our volume is, the volume, right, is increasing. If we're pouring in water, the height's going to be increasing with respect to time, and the volume is going to be increasing with respect to time. And so again, take the derivative of both sides. So derivative of V is 1, right? But we need to use the implicit differentiation chain rule in this case. So this is dv dt. And this is equal to, well, r squared is just a number that's not changing because r is not with respect to time, it's the height. And so treat it like pi. You're going to keep the pi r squared in there. So this is pi r squared. We're taking the derivative of height with respect to time. So the derivative of h is 1, but again, chain rule, so we're going to write the dh dt.
So for these, are we always going to be doing in respect of time?
So usually, yes. I can't think of a case where it's not usually with respect to time, but yeah, so with respect to time. So we're pretty much done, right? Because we already have dv dt by itself is equal to pi r squared dh dt. So we can clean it up a little bit if we wanted to. So part B was saying how is dv dt related to dr dt if h was constant? So pretty much the same sort of idea, but instead of maybe it growing height-wise, the height staying the same, but the radius is expanding out. And so that volume as the radius is expanding out is growing. And so that's what part B is kind of asking. So same sort of thing, but how is dv dt, the volume with respect to time, that rate of change related to dr dt if h is constant? So again, same kind of idea. We're just going to take the derivative. This time we're taking the derivative of v and r with respect to time, and we're treating h as a constant. I'm wondering. Okay. I know there's some way that I can move that text over, but I don't know how yet. So what do we have? V was equal to pi r squared h. So again, taking the derivative both sides, so we got dv dt is equal to, r now is with respect to time, h is a constant. So taking the derivative of r squared, so that's going to be 2r dr dt. All times, we still have our constants, pi h. So we could write it a little bit neater. So this is T2 pi r h dr dt. And last but not least, how is dv dt related to dr dt and dh dt if neither r or h is constant? So I'm going to actually add another page and do it on that. So again, we got v is equal to pi r squared h. Now, how is the volume with respect to time related to dr dt? and dHdt if R and T are neither constants. Okay, so basically we have your radius with respect to time. We have your height with respect to time. Notice radius squared times height. We're taking the derivative of both sides and we have multiplication between the radius and the height with respect to time. So we're gonna need to use the product rule here when we do this, as well as the chain rule. So maybe we should write that out before we start taking the derivative. So basically I'm taking the derivative with respect to t of the left-hand side v is equal to the derivative with respect to t of pi r squared h. So you have the derivative with respect to t of v is equal to, remember we can pull the constant out front. So pi times the derivative of the respect to t of r squared h. Oh, I just found out where color is. So we need the product rule. So we have derivative, I'm not going to take it yet, dv dt, our derivative with respect to t of v is equal to pi times. So product rule, we need to take the derivative of the first. So d dt of r squared times the second plus the derivative, or the first, which is r squared, times the derivative of the second. Okay, so the derivative of v with respect to t, well, derivative of v is 1 dv dt is equal to pi times, so the derivative of r with respect to t, so that is 2r, but this is dr dt, times h, the second. Okay. Plus the derivative of r squared, look at this, which is 2r. No, derivative of r squared, which we're not taking the derivative of the first, which is r squared, and the derivative of h. Derivative of h is 1, but it's dh dt. So we're pretty much done. We can clean it up a little bit. So in our case, the derivative of the volume with respect to time is equal to, well, we can distribute our pi if we want, and let's just put the dr dt and dh dt after each part of those terms. So this would give me 2 pi r h dr dt plus, so distributing my pi, so that gives me a pi r squared, and that's a dh dt. You guys okay? Trying to pick out a good one. Okay, so let's say the area A of a triangle with sides length A and B, enclosing an angle of measure theta is given to, so it's given us what the area of the triangle is. It's 1/2 times the length of side A times the length of side B sine theta. So how is the derivative or the rate of change of our area with respect to time related to the derivative of theta or d theta dt if A and B are constants? So how does the derivative of the area with respect to time relate to the rate of change of our angle if A and B are both constant? So this one shouldn't be bad at all. If A and B are constant, then basically we don't need to use the product rule. And we just have the constant 1/2 AB, and then we need to take the derivative of sine theta with respect to t. So same sort of process, take the derivative of A, it's with respect to t, so derivative of A is 1. So we have dA dt is equal to, so 1/2 AB, and so now the derivative of sine theta. So the derivative of sine theta, that one was cosine theta. And this was, and it's in terms of theta is with respect to t, so this is d theta dt. So I want to actually, no, maybe I don't have as much time. I'm going to go in more detail of a different problem, but let's just finish this one instead. Okay, so same kind of idea, but now it's asking how is dA dt related to d theta dt and dA dt if only B is a constant. So same idea, but now B is a constant, but A, that side is changing with respect to time. And so same kind of idea in this case, we have to treat, so we have A is equal to 1/2 AB sine theta. And so A is with respect to time and sine theta, theta is with respect to time. And so again, we're going to need to use the product rule. Okay, so derivative of A is 1. And with respect to time, so we have dA dt is equal to, okay, so A is with respect to T. So derivative of A, if I'm using the product rule, is 1. So I have 1/2 times 1 dA dt little a dt times B times sine theta plus, so I have 1/2 AB times the derivative of sine theta, which is cosine theta, d theta dt. And the last one was saying, okay, same equation, but now what do we do if A, B, and theta are all with respect to time? So we have A again is equal to 1/2 AB sine theta, A, B, and theta are not constants. So we're, like I said, we're going to have to do this multiple times. So maybe we can break it up where we say, okay, well, we can break it up like this, 1/2 times AB times sine theta. And so within the outer, we're going to need the product rule, right? But when we're looking at the derivative of 1/2 AB, again, we're going to need to use product rule. Okay, so the derivative of A with respect to T, well, derivative of A is 1, so this gives me dA dt is equal to, you guys okay, or should we rewrite it, write out all the steps? So we would have 1/2 times the derivative of A times B plus 1/2 A times the derivative of B. So that's just the derivative of the first piece times sine theta plus the first. So the first was the 1/2 AB times the derivative of sine theta. Okay, so I haven't even gone in and taken the derivative yet, except for the left. So the derivative of A with respect to T is equal to 1/2. Well, the derivative of A is 1 dt, dA dt. So I'm going to keep B there. And then for this piece right here, that was just 1 dA dt. Plus, so 1/2 A. But now when we take the derivative of B, that's just 1, but it was with respect to, this is dB dt. all times are sine theta out here plus 1/2 AB, and the derivative of sine theta is cosine theta. So I don't know how much we can clean it up besides just distributing the sine theta and writing it all in one color. I guess we could factor out a 1/2 from everything, but other than that, I think that's good enough. Okay, so that's the start of related rates, and we'll look more into different scenarios tomorrow. So for instance, if you have an oil spill in water and oil is pouring into the water, that's going to start expanding with time, the circle of oil. The radius is also going to expand in time. Can we figure out how fast your circle is expanding at time 20? Or maybe you were were told that you needed to figure out how to manipulate the camera to rotate as a rocket is shooting up into air, and you want to make sure that the camera is rising at the same speed and getting the picture of the rocket. And finding out the rate of change of the angle at a specific time. So we'll get more into more detail of word problems, but this just kind of gives you the idea of what we're doing, is that now we're taking the derivative with respect to time, and there's more functions, more than one thing that's relating to time, and so we're going to need to use implicit differentiation. So let me stop the video here, and then I can talk to you guys, and if you have any questions or any concerns, we can talk about it. Let me stop the video. Hold on.